So the next part was to draw a label diagram to show how total internal reflection works. Okay, so this is part 5 of 2017 question 7. Okay, total internal reflection. All right, so we have an interface here, and then we're going to draw. Okay, so this is, say, air and glass, and so it's easy to work with. All right, this is the normal. So that's just a 90-degree line is what that means. That's a normal. I'm going to draw some different colors here. Okay, so this is the incident ray, and then this is going to be the refracted ray. All right, so light is coming in here. Now let's go back to my black. Okay, so the incident ray is this. And this is the refracted ray. Refracted, not reflected. Well, it could be reflected as well, actually, because it's been. It's probably better to say reflected, actually, now that I think about it, because it's being reflected back in. It's not refracted. Total internal reflection. Okay, so this here is our angle of incidence, and this is going to be the angle of reflection. And this happens when I is greater than C. C is the critical angle. Let me just go back. Draw a label diagram to show how total internal reflection. Okay, so to show how total reflection. Okay, yeah. Total, just going to write a quick sentence just to have it. Oh. When the angle of incidence is greater than the crit. Oh, I can't write it all today. Oh wow, that's meant to say critical. The critical angle for that material. Okay. The next bit was draw a label diagram to show how an optical fiber transmits light along its length. All right, so this is fairly straightforward, I hope. Just going to draw this. Oh no, that's bad. I'm going to draw there, and this is the. Why can I not write today? This is the fiber optic cable. And I'm just going to say that this is light. So it bounces along like this. And they designed the cable so that it's very hard for it to be not reflected back in. So this is light, like that. Okay. Yeah, that's all I really need. A label diagram. Yeah, that's fine. Okay, an optic fiber cable has a refractive index of 1.5. Calculate the angle at which total internal reflection occurs. Okay, so the refractive index is 1.5, and we know that the refractive index is also 1 over the critical angle. All right, so I need to rearrange this to find the critical angle. So the first thing I'm going to do is multiply both sides by the critical angle and divide by the refractive index. So essentially, it looks like I swapped these. The last step is to find the C by itself. I need to do sine inverse of both sides. Okay, I do sine inverse of over here, and it gets rid of the sine. And then I do sine inverse of the right-hand side as well. Okay, so back up here, it's sine inverse of 1 over 1.5. Okay, and my calculator, I do second function sine, that's how I get my sine inverse, and then 1 over 1.5, close my brackets, and I get an answer of 41.81 degrees. Okay, that's the critical angle for that material. So I multiply both sides by sine C, divide both sides by n, which is what, what got me to this stage, and then I do sine inverse of both sides and put in my number, and then I get my critical angle. Done.